You know that feeling you get sometimes when you're using an LLM? That little moment of shock where it does something unexpected? It doesn't just repeat facts, it actually seems to get it. It solves a problem it's never seen before. Well, what if that's not just a clever trick? What if there's a hidden learning process happening right there in the forward pass? A secret learner inside the machine. So let's peel back the layers and see what's really going on.
And that brings us to this huge counterintuitive question. See, we've gotten really, really good at teaching machines to recognize patterns. You just show it a million pictures of a cat, and eventually it knows what a cat is. But reasoning? How do you teach a machine to actually think, to connect ideas, to solve a brand new puzzle all in an instant? That's a whole different ballgame.
Okay, so this isn't just a philosophical question. Check this out. This table shows some pretty jaw-dropping new data from OpenAI. On the left, you've got GPT-4o, which we know is an incredible model. But on the right is their new model, o1. And just look at these numbers. For Math Olympiad problems, the score jumps from 13% to over 83%. For competitive programming, it leaps from the 11th percentile to the 89th. This isn't just a small improvement. This is a quantum leap in the ability to do hard, multi-step reasoning.
And we can actually watch this happen. Here, the O1 model is given a cipher it's never encountered, and instead of just guessing, look at its process. It's methodical. It observes, it counts frequencies, it forms a hypothesis. Maybe each letter in the original text is represented by 2 letters in the code. Then it tests that idea, confirms the pattern, and just systematically cracks the whole thing. What you're seeing is the blueprint of a thought process. This goes way beyond simple pattern matching.
So this is amazing, right? This new level of reasoning power is a huge deal. But the second we try to take this power and apply it to a complex, messy, real-world job, like, say, being a software engineer in a big company, we slam right into a wall, a giant, invisible wall made of one thing: context. I mean, think about how a human developer actually works. They're not just looking at the code in front of them. They're plugged into this entire stack of unwritten knowledge. The task description, yeah, but also which tools to use, the grand architecture of the codebase, why past decisions were made, that's all in the Git history, teen style guides, and all that tribal knowledge that only exists in old design docs and Slack channels. You drop an AI agent into that environment cold, it's flying blind, completely lost. And the first thing everyone thinks is, oh, simple, just give it a bigger context window, shove all the docs in there. But that's a trap. As researchers at Factory.ai point out, it's not about the sheer amount of context, it's about the quality. A bigger window without careful curation just makes it easier to drown the model in useless noise. It's like trying to find a needle in a haystack by adding more hay. The real key is curation. So let's say we do that. We give the model that perfectly curated, high-quality context. How does it actually use it to reason? Well, this question leads us to one of the most remarkable abilities these models have, a way of learning that happens in a flash with zero retraining. The name for this is in-context learning, or ICL, and it's exactly what it sounds like. It's the model's ability to learn a totally new skill just by seeing a few examples that you put right there in the prompt. But here's the kicker, the part that seems impossible. None of the model's core programming, its weights, changes at all, not one bit. It's somehow learning without actually learning. Let's make this concrete with a super simple example. First, we give the model an instruction, translate English to French. Then, we give it just one example, a little hint. Sea otter becomes loutre de mer. Now we give it a new word it hasn't seen in this context, cheese. And what does it do? Bam, fromage. It learned the entire task, on the fly, from that single demonstration. Okay, I know what you're probably thinking right now. Come on, that's just incredibly sophisticated pattern matching. And you're not wrong to think that. For years, that was the standard explanation for this kind of behavior. But what if that's the wrong way to look at it entirely? What if something much more profound, something that looks an awful lot like real learning, is happening in those few milliseconds of the forward pass? To see why this is so weird, let's compare it to how we normally train a model. On one hand, you have traditional training with gradient descent. The best analogy is a blindfolded hiker trying to find the lowest point in a valley. They take one slow, careful step at a time, feeling for the downward slope. It takes hours, days even. And every step they take permanently changes their position. It's slow, methodical, and permanent. On the other hand, you have in-context learning. It's like a flash of insight, instantaneous, and totally temporary. It's gone the moment you ask the next question. They seem like polar opposites, right? This is the moment where everything clicks into place, because recent research has uncovered a stunning, almost unbelievable connection between these two worlds, a hidden mathematical bridge. This is where we discover that the attention mechanism, the heart of every modern transformer, isn't just about paying attention to words. It's actually a powerful optimization algorithm in disguise. And here it is, the bombshell finding. Research has shown that the process of in-context learning that happens inside a single attention layer is strictly equivalent to performing one step of gradient descent. Let me say that again because it is so important. It's not like gradient descent. It's not an analogy. It is a mathematical identity. The model is, quite literally, performing an optimization step every single time you ask it a question. So how on earth is this possible? Well, the core idea is this concept of a dual model. When you feed the model those examples in your prompt, the attention mechanism uses them to build a tiny temporary model inside itself. Think of it as a little pop-up learner. This is our secret learner hiding in plain sight. And for that one single request, the model performs a quick one-step training session on this mini model to get you your answer. It's literally learning on the fly. If that's a bit too abstract, we can think about it geometrically. Imagine a huge invisible space of all possible answers. What the attention mechanism does is it takes your examples and uses them to figure out which direction to face in this giant space. Then, with a single perfectly calculated step, it moves in that direction, boop, and lands right on the correct answer. It's an optimization step in a vast conceptual landscape. And if you're still not convinced, look at this. This chart is, well, it's just beautiful. It's the smoking gun. The solid green line shows how a simple model's error goes down as it learns, step by step, using traditional gradient descent. The blue dots, that's the error rate for a transformer, with each dot representing one more layer. And look, they lie perfectly on top of each other. They are identical. This isn't a coincidence. It's undeniable proof that each layer of a transformer is effectively performing one more step of learning. Okay, let's take a breath. We just went deep into the mechanics. So now that we have this incredible new mental model, this idea of a secret learner, let's circle all the way back to the beginning. How does this explain that massive leap in reasoning we saw with the O1 model? Remember that step-by-step thinking it did to solve the cipher? That chain of thought? Well, it turns out that's not just the model thinking out loud for our benefit. It's the literal, visible trace of this internal layer-by-layer optimization process. Each step it rates out is another turn of the crank on its internal learning engine, refining its answer as it goes. And this insight, it changes everything about how we should work with these models. Prompt engineering is no longer some dark art of finding magic words. It's the science of creating a high-quality, miniature training data set for this internal learner. Context management? That's just data cleaning and preparation for the learner. And safety alignment? That's just giving it the right safety-focused examples so it learns to optimize for helpful and harmless answers. So, what do we do with all this? This isn't just a cool theory. It gives us a whole new set of rules, a new toolkit of mental models for how to think about and build with these incredibly powerful systems. Okay, here's the first big takeaway. Every time you write a prompt that includes examples, you need to stop thinking of yourself as someone asking a question. You need to start thinking of yourself as a machine learning engineer crafting a tiny, perfect micro-training data set. The quality, the clarity, the relevance of those examples you provide, that directly determines how well the secret learner gets trained for that specific task. Second, and this one is the real mind bender. We used to think of the forward pass, the act of generating a response, as a static process, like looking up a fact in a giant pre-written encyclopedia. That mental model is officially dead. The forward pass is a dynamic, real-time optimization process. The model isn't just retrieving an answer. It is actively learning and computing the best possible answer for you in that very moment. And that leads directly to our final takeaway. That incredible, complex reasoning we saw from O1 at the start, the math, the code, that wasn't just something it memorized from a textbook during its initial training. It was being computed fresh, on the fly, by this internal learner that we now know exists. The model is figuring it out, not just looking it up. And this whole discovery leaves us with a truly staggering question for the future. We've just learned that the attention mechanism, the engine of the entire modern AI revolution, is secretly implementing gradient descent.
But let's be honest, gradient descent is basically the first, simplest optimization algorithm we learn about. So what happens when we stop accidentally building these learners into our models and start designing them on purpose? What happens when we invent new architectures that explicitly embed other, even more powerful learning algorithms right into their core? What kind of secret learners will we build next?